So I'll pass this slide. Well, first a brief summary of what I'm going to present today. First, the motivation, and then the objectives of the work, and the physical and mathematical modeling, then the solution methodology, and results and discussion, and the conclusion. Well, first, the motivation. The main motivation is based on the AF447 accident. Here we see the icing on pitot probes. This one comes from Tesagi in Russia, and this one is an old test done by NASA. You can see that the ice is concentrated on the stagnation point and on the support, but the support is not that functional on those probes. So the main portion that we should look at is the stagnation point, this end here. Well, we had some accidents, not just the AF447 that were linked to icing of pitot probes. There were several others. I can remember two of them. One from Northwestern. I think it was going from the Dominican Republic to the United States, and another one from Argentina to Chile. The investigation pointed out that icing of pitot probes were one of the reasons of the catastrophe. Well, basically that's the certification envelope of the standards of today. This is altitude and ambient temperature, and we see here that there are some incidents outside of the envelopes. He said today about the standards being modified. Probably they will ask them to comply with these incidents, but for today, no one, at least I think no one does that, and this shows the need for doing it. Well, but not just that, aerospace industry is now moving towards extensive use of composite materials. These composite materials, they tend to participate more on the heat transfer, on the heat transfer occurring on the surface of wings, of empennage. We have two examples here. The Boeing 787, it's already flying. It has about half by weight of material, of composite materials using. He's using 50% of composite materials. And the Airbus 350, they promised it will be 53% composite, but we don't know yet. It's not operational. Well, the importance here, so is to show the importance of taking into account the mutual influence between the heat transfer in the solid and in the fluid, and to establish mathematical models for the thermal analysis of the surface, and in the future of ice accretion over the surfaces in the icy wind tunnel that we saw yesterday. And to physically analyze and propose some modifications, some simple modifications that could be done that will render the both pitot tubes or wings or anything like that more reliable under icing conditions. First here, for the pitot tube, we used this model here. I think it was already shown. It's the same one that's on the icy wind tunnel. We borrowed it from the Brazilian Navy. It's an old design, but it didn't change that much. Basically, it's the same design since Pitot developed it in the 18th century. So there is no problem to use it as an example. Well, the heat conduction in the solid here, we use cylindrical coordinates, nothing too away from. Well, here we have some conditions. The stagnation point, we used a heat transfer coefficient from the literature, correlations basically, and for the coupling between the solid and the fluid, it was used. Here we have this H here, this heat transfer coefficient that will be calculated iteratively between the fluid and the solid, that I will explain a little bit more later. Here is the entry data. We have some serious variations, abrupt variations of the geometrical properties and thermophysical properties, because this first one, here we have the front cone, and then we have a cylindrical part, and then that wing-like portion that is the support, and the same here for the perimeter. And this is the most important one that I want to talk about. It's the thermal capacity. We see here that as we move in the probe, we get this step function, and that is due to the presence of electrical insulation. We have an electrical thermal protection system in this probe, and for the guy that handles it, not to be electrocuted or something like that. Not electrocuted, it's not that big, but he would feel a little discomfort. It has an electrical insulation there, and the thermal capacity of this thermal insulation is huge. The heat conductivity is not that big. It's an insulation material after all, so it's almost unnoticeable here. But this guy here, it plays a main role in the transient. Guilherme talked before me that the transient for pitot tubes is very, very important. So taking this guy into account, we saw that made a big difference in the transient response that we found. So here is the Joule effect from the thermal protection system. You see that the step here is almost in the same place as the one in the heat capacity. And here we have the boundary layer equations that were used for the fluid that were flowing over the pitot probe, and nothing away from the open literature. Here we have a total enthalpy equation that is more convenient for compressible flow that we are using. I'm not going to take a long time here. And now talking about the airfoil, I started the other way around. The airfoil is the geometry is more smooth. It's not that abrupt as we had with the pitot probe. But the equations are almost the same. This is mechanical boundary layer and a turbulence model. I'm not going to talk a lot about this for the presentation to not be more boring than already is. And here is the really new thing about this. I talked about the mutual influence between the solid and the fluid, But it's too complicated, like I said, with the pitot tube to have two models and try to solve them all together and try to make the fluxes and the potentials here to be continuous. So one approach proposed here is to solve it all together and make the transition between them basically a transition between thermophysical properties. An abrupt transition, we called it single domain formulation. Actually, we published a paper recently about this. And here is the model that is capable of representing all the physics occurring in both solid and in the fluid. Well, here is the solution methodology. I'm not going to open the mathematical problem there. It would be too long. The presentation would be too long if I did that. So I'm just describing which I used. For the pitot tube, the solid is solved using GITT is a hybrid method that Professor Cotta helped to develop. For the fluid, it's just integral method from Karman Polhausen. It's very simple, and the main problem with that was the need for iterative process. These two problems are too different mathematically. It's too difficult to solve them all together. And so we found no way around of using an iterative process that basically takes the results from here and then goes to the fluid and then comes back. This is very time consuming. But now for the airfoil, we are proposing the single domain formulation solved by GITT, as I already said it. It's more straightforward and it eliminates the need for iterative processes because the model itself makes the continuous conditions now results and discussion first in the wind tunnel in Metro. We used thermography to measure the temperatures along the pitot tube. This is the same pitot tube that you saw. And this here, this picture it's not good. We almost can't see it, but it's a PIV image of the pitot tube inside the wind tunnel. And here are the results with taking this line here, this line, and we take the temperature there, the temperature at the surface. This is the red curve, the temperature along that line, the X here. And this black curve is the results that we obtained with the model. You can see that the adherence is almost perfect here. Here in the support is not that good because probably we didn't take into account all the losses there. But the support, as I told you before, is not the main portion that we are looking at. So we found that very satisfying, the results obtained with this model. This is just some other results of the integral method. We got here transition. It was used abrupt transition. We didn't use a finite length of transition. And here the heat transfer coefficient. I'm not going to talk too much about this. Now an important result. The first one here is these are temperatures for several sections of the pitot tube. A long time-wise here, we can see these results are without considering the heat capacity of the porcelain. And we see that the blue curve is the model and the red curve is the measurement. we see that we underestimate the time to get to steady state. And now, considering the porcelain, we get much better results. And underestimating the time to reach the steady state temperature, the high temperature, could lead engineers to make bad decisions. Because the accident with the AF447, it took like 4 minutes, if I'm correct. I don't know, 4 or 5 minutes. If your thermal protection system takes more time than that to melt the ice, you will simply do nothing. The accident will occur whether it's on or not, if it's working or not. Now the A4 Skyhawk flight test in the base of the Brazilian Navy there at a city called São Pedro da Aldeia. Here we have the P-22 positioned in the front cone of the aircraft, and they positioning there. Well, it's basically the same result. We asked the pilot to turn on and off the heating system of the thermal protection system, so we could see those transients and see if we can follow them adequately. And these results, here we have the comparison again about with porcelain and without porcelain. You can see that the same effect, the underestimation of the time to reach steady state, is present here also. We got here in blue, we have temperature with time. Here in blue, we got the measurements made with thermocouples, and the black curves are the model. The black curves in both graphs are the model. The model developed. We have another model that was developed by Zé Roberto that was here yesterday. I don't know if he's here now. And we got very good results, even for an uncontrolled situation with the model, which we found was very good. This is basically the same test, but in another altitude. I will not talk too much about this. This is an important graph. As I said before, one of the objectives was to conclude about the mutual influence between the solid and the fluid, and here we see why. This is in Portuguese, but I will tell you what it means. The red curve is basically, I don't want to know how the flow goes. I don't want to know about that. I will use a correlation to do this calculation. And the black curve, it solves the two physics altogether. And as we can see here, the basic approach is much simpler to simulate. It overestimates the temperature, especially at the stagnation point. That is the critical point for us in pitot probes. So again, this could lead engineers to make bad decisions. Here, the heat transfer coefficient, we have a short time. I'm not going to stop there. And finally, we did some parametric design studies, first with power density. Well, why should the wire give a constant heat generation all over the portion that it resides? Why not gives in a straight line or an exponential? Because we need the heat near the stagnation point. Here, if it's hot or not, we don't care that much. It could lead to ice formation here also. But the main functional concern is on the entering of the pitot tube. We don't want blockage there. So we propose this, and the increase with a fairly small modification of the profile of the distribution was already kind of significant of 2%. It's not that big, but it's just a straight line with a slope that was not that changed from the constant. But now here comes the big star, a fully cylindrical probe. Why they put that cone in the front of the pitot tube that we were using as a model? Well, doing a cylindrical probe is probably much more easy to be manufactured, and well, let's give it a try. And not just that, not just the cylindrical portion. If we have a cylindrical portion, we can pull the thermal protection system more closely to the stagnation point. That's where we want the heat to go. And the results were amazing. 26% just by doing that. 26% in increase of temperature there. This raises some questions. The manufacturers of those probes, they do the analysis they should. Do they do that? Because it's simpler for them to manufacture the probe purely cylindrical. Why the hell do they put the cone there? They could say, it's more aerodynamically efficient, but near to the drag of the whole plane, that's nothing. The drag of the pitot tube is nothing near the drag of the rest of the plane. Basically what this says to us is that they don't care that much about the thermal behavior of the pitot tube, because if they cared, this is fairly simple analysis. It doesn't take too long to simulate, and I don't know why they do that. I don't know. They simply don't care. That's my opinion, basically. And now for the airfoil, I have some basic results, just for showing that it works. I'm running some simulations now as we speak, basically with the wall with a constant heat generation. And here we have the transition to the fluid. We have the interface around here. And this is done all together in just one model, just one system to be solved. And it works pretty well, as we are going to see in the next graph. The bold symbols, they represent the old-fashioned way to do it, to couple, the old-fashioned, to couple with correlations. And the ones in white are the new ones. And again, we see the overestimation of temperatures that we saw in the other comparisons between conjugated and correlation-based simulations. But the agreement was very good, as far as I can tell, and it gives far better results with much less time to do the simulations, to run the simulations. Here is just for laminar boundary layer. I had some problems with the turbulent, but I already solved it. But, well, the conclusions now: a physical and mathematical model capable of reproducing the thermal behavior of aircraft surfaces was built and validated, both in controlled conditions, inside wind tunnels, and in real conditions, in flight. that was very important. It gives us confidence that what we simulate will correspond to reality. It's not just a number that we calculated that means nothing. Now we concluded about the wall participation importance in both the transient and now in the steady state. As I said, that graph back there, it overestimates the temperature there. In icing analysis, this is critical. You could easily jump from a reliable condition to an unreliable condition. And in the transient, the participation of the heat capacity is huge also. You underestimate the time to get to steady state, to get to the high temperatures. And this kind of accidents, they happen very fast. You cannot afford to have long transients. You want to get the result fast. And the analysis performed allowed us to discover some design paths that manufacturers can take to improve their sensors. I don't want to believe that they don't think they can improve it. So they should do this analysis because we shown here, I was just an undergraduate when I did this. An undergraduate showed them that they don't do the analysis. But that's basically. I'm no genius. I'm no, and I showed them. Why the hell do they do the cone? I don't know. If someone knows, you can tell me. I don't know. Well, thank you for the attention.